This recording is for Geometry B, Unit 1, Lesson 3. We're still reviewing Geometry A, so that's what we're doing. This particular lesson is on logic and proofs. A very fun topic, I'm sure, for most geometry students. It's one that gives a lot of students trouble. It's really a case where you want to be exposed to as many different possible proofs as possible. But I'm going to basically do a quick summary or review of the material, hopefully to bring some things to mind. It's by no means exhaustive or detailed. All right. All of logic is built on this basic idea, that of a conditional statement. And it helps if I were not drawing in black ink. Right? Conditional statement. A conditional statement, an example is, if I have a dog, then I have a Dalmatian. Okay? There's an if part and a then part. The if part is called the hypothesis. This is not the same as a scientific hypothesis. Okay, it is the condition that must be met for the conclusion. Okay, the then part is called the conclusion. So the geometric hypothesis, the logical hypothesis, I have a dog, is conditioned enough to conclude that I have a Dalmatian. Right? Now you may think about this, and whether or not this statement is true. Okay? If I have a dog, do I necessarily have a Dalmatian? And the answer is no. So the truth value is false. This is a false statement because I can think of one counterexample. I can think of many counterexamples, but all it takes is one counterexample. And for a counterexample, I'm going to think of something that makes the initial statement true, but the conclusion false. The counterexample would be a German Shepherd. German Shepherd. A German Shepherd is a dog. It makes that statement true. A German Shepherd is not a Dalmatian. It makes that statement false. So it satisfies the hypothesis but not the conclusion. Therefore, it is a counterexample demonstrating that the statement is false. Okay? Conditional, if-then statement. Hypothesis, the if part. Conclusion, the then part. Counterexample is one example that makes the hypothesis true and the conclusion false. Okay? Now there are variations on this conditional statement. Okay? And I'm going to write this way. I'm going to write this A implies B. A implies B. Okay? The variations on a conditional statement are this: the converse. The converse of A implies B is B implies A. So I would write, for the converse of the original statement, if, and I'm going to shorten this, I'm going to leave if I have a, if Dalmatian, then dog. Notice this has a different truth value, right? If I have a Dalmatian, the if part, then I have a dog. This happens to be a true statement because all Dalmatians are dogs. And we can represent this by this Venn diagram. If we have the set of Dalmatians, they are a subset of all dogs. The hypothesis, if the hypothesis is a subset of the conclusion, then the statement has a truth value of true. Okay? If not, then it is false. Right? So Venn diagrams can be used to make sense of it. Converse, when we switch the if and then part. Okay? Then we have the word inverse. Okay, the inverse of A implies B is not A implies not B, and I'm using the tilde character to indicate not. This is the word not A. So here's what the statement looks like. The original statement: if it is not a dog, then it is not a Dalmatian. Okay, so that's the inverse, and you can think about the truth value of this particular statement. If it's not a dog, then it's not a Dalmatian. That happens to be true. If it's not a dog, it's not a Dalmatian. So if it's outside the set of all dogs, then there's no way it can be in this set of Dalmatians, because Dalmatians are dogs, right? So that's a true statement. Inverse. Okay, and then we have the phrase contrapositive. Contrapositive. And A implies B, it's contrapositive, switches the order and negates both. So not B implies not A. So the contrapositive of the original statement, if I have a dog, then I have a Dalmatian, is if it is not, if I don't, or if it's not a Dalmatian, then it is not a dog. Now think about the truth value of that. If it's not a Dalmatian, it's not a dog. Can you think of something that's not a Dalmatian but is a dog? Well, the German Shepherd comes to mind. This has a truth value of false. And one of the interesting things about contrapositives is they always have the same truth value as the original statement. That is, they are logically equivalent. If I have a dog, then I have a Dalmatian is the logical equivalent statement to if I don't have a Dalmatian, then I don't have a dog. Okay. It can be the original statement is if I'm in the set of dogs, then I'm in the set of Dalmatians. If I'm not in the set of Dalmatians, then I'm not in the set of dogs. All right. Hopefully that makes a little sense. I know it can be a little confusing. All right. There's one more phrase we need to use, and that's biconditional. Biconditional. And the symbol for that is A implies V, but also V implies A. And the way we write it is this. It is a Dalmatian. It is a Dalmatian if and only if. If and only if, and we often in mathematical circles we simplify that to IFF. So IFF stands for if and only if. It is a Dalmatian if and only if it is a dog. And that is a way to write two statements in one. It's a Dalmatian if it's a dog. It's a dog if it's a Dalmatian. Okay? And this, of course, has a truth value of false, because it needs to be true both ways, both directions, and it is not. German Shepherd is not a Dalmatian, but it is a dog. Okay? All right, so biconditional. So a biconditional is something that's true forward and backward. Let me give you an example. If, or I should say, x plus 2 equals 5 if and only if x equals 3. So if x plus 2 equals 5, subtract 2 from both sides, then x equals 3. If x equals 3, then x plus 2, 3 plus 2 equals 5. It flows both directions. So it is true both directions. So it is a biconditional. X plus 2 equals 5 if and only if x equals 3. Okay, and then one more thing, and this is the funnest part, proof. Right? Well, we're going to do an example of a proof, and to do an example of a proof, the best example I can think of is the proof of the vertical angle theorem. So let's go ahead and do that here. Let's get a new slide. Okay, vertical angles are defined as two angles sharing the same vertex whose sides form opposite rays. Or more loosely, you can think of it as angles formed by two intersecting lines that are across from each other. So angle 1, angle 2. But I'm going to put angle 3 right here. Okay? Right, so we're given the drawing. Given the drawing. We want to prove that the vertical angles are congruent. So prove angle 1 is congruent to angle 2. Okay? And we have, I'm going to do a 2-column proof. On the left column are reasons. Okay? Or statements. The left column are statements. And the right column are reasons. And we always start, if you have trouble with a proof, always start with the given. Okay, we have the information in the drawing. Okay, which is given. We always end with what we're trying to prove. Now, what am I trying to prove? I'm trying to prove angle 1 is congruent to angle 2. Okay? So let's go there here. All right, so statement number 2. Angle 1 and angle 3 are a linear pair. How do I know? That's what a linear pair is. That's the definition of a linear pair. Okay? Statement 3, same thing. Angle 3 and angle 2 are a linear pair. How do I know? Definition. Notice every statement gets a reason, linear pair. Okay? Statement 4, the measure of angle 1 plus the measure of angle 3 is 180. And I'm going to combine these. The measure of angle 5, line 5. The measure of angle 3 plus the measure of angle 2 is 180. Okay, so the reason for 4 and 5 combined is linear pairs are supplementary. That means they add to 180. Okay, line 6. They both equal 180. So if they both equal 180, they're equal to each other. Two things equal to the same thing are equal to each other. So I'm going to write an equation that says the measure of angle 1 plus the measure of angle 3 equals the measure of angle 3 plus the measure of angle 2. What rule says that? The rule that says that is called the transitive property, which says two things equal to the same thing equal to each other. Transitive property. Okay, so now I'm going to subtract the measure of angle 3 from both sides. Measure of angle 3. Using the rules of solving equations. So 7. We get measure angle 1 equals the measure of angle 2. And what rule says that? Well, we just subtracted from both sides, so it's called the subtraction property of equality. Subtraction property of equality. All right, so now we're ready for line 8. I just have had enough room. Okay, if the measures are equal, the angles are congruent. Right? So 8, what rule says if the measures are equal, the angles are congruent? That's the definition of congruent angles. Okay, and QED, quod erat demonstrandum. I said it. Therefore, I demonstrated or proved it. Quod erat demonstrandum. Extra points if you can remember that. Little Latin. One of my college professors used to end his proofs with "Wad." We are done. Another common punctuation at the end of a proof is a shaded in parallelogram or rectangle at an angle. Okay? All right, so that's a proof. Note a couple of things about the proof. There's a drawing, there's a given, there's a proof. The proof typically starts with the given and ends with what we're trying to prove. If you can do that much, you can get partial credit on essay questions. Okay? And two-column proof has statements on the left and reasons on the right. Okay? And it logically flows from one argument to the next, to the next, to the next. All right, that's it. Hopefully that helps. I know this is some tricky stuff. Don't hesitate to book a live lesson. I'm happy to go over this individually with you.